So this will be the first lecture over Chapter 7. So Chapter 7 is over alkenes. So we'll look at how to name alkenes, the basic properties of alkenes, and then the reactions, some of the reactions that make alkenes. So the E1 and E2 mechanism. So in this lecture, we'll just look at how to name alkenes. Okay, so if we take these two molecules to start with, so they're both 1, 2, 3, 4, 5 carbon chains. So they're both would be pentane derivatives. To name a molecule as an alkene, take the alkane parent and change the A ending to an E. So it would be a pentene. But then we need to specify where the double bond is at. We would number the molecule to keep the alkene as low as possible. I'm sorry, there should be a CH3 there. So let's see. So in the first molecule, the double bond starts at carbon number 1. So we would name this pen. So the E is what tells you it's a double bond. So put the 1 right before the E. So that would be pent 1-ene, and then this would be pent -2-ene. So this is the more conventional way to name alkenes. The older way to name it when I first learned organic chemistry is to put the 1 at the front of the parent. So that would be 1-pentene and 2-pentene. And so you see that done still all the time, but putting the 1 right before the letter that tells you that it's an alkene is the more conventional way to name things, and that's the way that I prefer that you do it. Okay, so if you have an alkene, then we've talked about the stereoisomers before, cis and trans. Or you can have groups on the alkene arranged differently in space, spatially differently. So these next few examples illustrate that. So if we take this molecule and want to assign cis and trans to it, the way that this is done is you split the double bond in half and assign priorities just like you would do if you were doing RNS. So on the right side of the double bond, we go to a chlorine versus a carbon, and chlorine has priority over carbon, so this is number 1, and this pathway is number 2. And then you go to the other side of the double bond and do the same. We have a bromine versus a carbon, and it's based on molar mass. So bromine has a higher molar mass than carbon. So this is number 1, and this is number 2. And then the ones are opposite across the double bond, so that would be the trans isomer. So this molecule we can name because we know how to name all of the pieces of the molecule. So if we were to name this molecule, so we want to number this molecule to keep the double bond as low as possible. So this is going to be carbon 1, 2, 3, 4, 5, and 6. So it's based on a hexane parent. And then we would change the A to E, so it's going to be a hexene. And the carbon-carbon double bond starts at number 3, so it's going to be a hex 3-ene. And that's going to take care of basically all of this. And then we have to name the substituents. So on carbon 3 there's a methyl, on 4 there's a bromo, and on 2 there's a methyl. So alphabetize those. So 4 bromo, 3 chloro, and then 2 methyl. And so that takes care of the substituents, and then we still have to take care of the stereochemistry. And the stereochemistry will come in the front of the name, so this will be trans. So in parentheses, put the stereochemistry at the front of the name, so trans 4-bromo, 3-chloro, 2-methyl, hex 3-ene would be the name of that molecule. Okay, so for the next molecule, we haven't learned how to name ketones and thiols yet, so we won't worry about naming it. Let's just classify it as being cis or trans. So again, we split the double bond in half and then assign priorities on the right and the left. So on the right, that carbon is number 1 and hydrogen is number 2. So we just do 1 and 2 on both sides of the double bond. And on the left side of the double bond, so we go to carbon and carbon. That's the same, so we need to go to the next group. So this carbon goes to a sulfur, a hydrogen, right, because there's a hydrogen attached to that carbon. So that's the hydrogen I'm talking about, and a carbon. And attached to this carbon is 2 oxygens, because we treat the double bond like 2 single bonds, and a carbon, right, that carbon, and 2 oxygens because of the double bond. So oxygen, oxygen, carbon versus sulfur, hydrogen, carbon. And you don't add things up. You simply look for, of all of those things, what has the highest mass, and it's sulfur. So this is going to be priority 1, and that pathway is number 2. So here the ones are on the same side, so that's going to be cis. So you also see what's known as the E and Z way of classifying this. So trans is the same thing as E. It's from German, gegen, which means opposite or trans, and the cis is the same thing as Z, which is also from German. Z means zusammen, which is the same thing as cis. Cis are the same. So you see cis and trans, E and Z used all the time in terms of naming alkenes. But E and Z should never be used for rings. Let's see. So if we had this, for example, so that would be cis, right? Not Z. So E and Z only used for alkenes. So it's only used to describe the stereochemical relationship around the alkene, not cis and trans. But cis and trans is used for both rings and alkenes. Okay, so for this molecule, so if we split the double bond in half and assign priorities, well, on the left side, you have the same group, 1 and 1, so you cannot assign stereochemistry there. There is no cis and trans for an alkene like that. And if we were to name this alkene, so we keep the alkene as low as possible. So the left is carbon 1. So this would simply be 4-iodo. 4 carbons would be butane. Change the A to E. So butene, and the carbon-carbon double bond starts at carbon number 1, so that would be 4-iodo but 1-ene would be the name of that molecule. Okay, so this one, cis and trans, so we split the double bond. That's going to be number 1, and that's going to be number 2. Right, so we go to carbon and carbon. Those are the same, so you go to the next positions, right? This carbon would go to have 3 hydrogens attached since it's a methyl, and this one would have 2 hydrogens and a carbon attached. And on the right side, we go to carbon and carbon. That's the same, so we go to the next position. This carbon has 2 hydrogens and a carbon attached, so this carbon goes to HHC, and this carbon has a hydrogen and 2 carbons attached. So this carbon goes to CCH. And so CCH beats HHC, so this is number 1 on the bottom and number 2 is on the top. So it does not matter that the iodine is there, and the iodine has the highest mass, because you go in order, and as soon as you find a difference, you stop. So you find a difference at the first carbon. Well, you find a difference at the next, when you go from the first carbon to the next position. So the 1 is on bottom on the right, whereas the 1 is on the opposite side of the double bond on the left. So this would be an example of a trans alkene or an E-alkene, right? So we could name that one because you know how to name that, but for time, we'll skip naming that molecule. So this one, if we wanted to assign cis and trans, so that's 1, that's 2. Now on the left, so you don't always have to show hydrogens on carbon, so the hydrogen, so that carbon on the right side of the double bond has a hydrogen on it. In order to get cis and trans right, you have to know spatially where that hydrogen is at. So is the hydrogen down here? Because if you did that, you would do 1, 2, and then ones would be opposite, that would be trans. Or is the hydrogen up here? And if you did that, then the ones would be on the same side, and that would be cis. So where's the hydrogen at? Well, that if you understand what the geometry is around that carbon, it's sp2 hybridized, right? So it's trigonoplanar. So what are the bond angles if it's trigonoplanar? The bond angles are 120 degrees. So if you started here and went there, that's 120 degrees, that's where the hydrogen is at. The hydrogen is not down here, right? Because that would not be the appropriate bond angle. So the hydrogen is not down here, it's up top. And so now the ones are on the same side. So this is an example of a cis or a Z alkene. Okay, so on the next molecule, so again, you have to know where hydrogens are at. So this hydrogen is up here, and that hydrogen is down there. Of course, that just looks the best as well. So sometimes that helps you get the right answer in chemistry, what looks right. Because if you put the hydrogen down here, well, hopefully that doesn't look right to you. Or if you put this hydrogen up here, hopefully that just doesn't look right to you. But you can know where the hydrogen is at based on bond angles, because each carbon is sp2 hybridized trigonoplanar, so you got to have 120 degree bond angles. Right, so that's 120. That would be 240 and 360. And you're back to where you started at. Okay, so if we assign priorities, so split the double bond. So this is 1, this is 2, and this is 1, and this is 2. Ones are opposite, so this would be a trans or an E alkene. So let's name this one. So what do you do if you have 2 double bonds? So that drawing's getting a little messy. Let me redraw it right quick. Okay, so if we have 2 double bonds, so we're going to number this from this carbon. Because then the first double bond starts at carbon number 1, whereas if you started numbering from the right, the first double bond would be at carbon number 2. And we want to keep the numbering scheme as low as possible. So we have a 1-bromo. We should also recognize this alkene. There is no cis and trans, right? Because on the right side, you have 2 1s, 2 of the same thing, so there's no cis and trans possibility there. Okay, and so the first double bond is trans, so we could say 1E, for example, or we could say 1 trans. Whoa, whoa, whoa. Okay, so we have first double bond is trans, so 1E, and then 1 bromo and 4 methyl. So the parent would be 5 carbons, so that would be pentane. So to make this easier to say, the A is typically kept, and you just stick a diene there. So then this would be penta 1, 3. So the double bonds start at carbon number 1 and carbon number 3. So penta 1, 3 diene would be the name that molecule. So 1 double bond would be diene, 2 double bonds triene, 4 double bonds tetraene, 5 double bonds pentaene, and so forth. Okay, so if you have a double bond in a ring compound, so parent would be cyclohexane, change the A to E, so this would be a cyclohexene. And technically it would be, well, so by default, the double bond has to be at carbon number 1, start at carbon number 1. So it would be common to not put the 1 there. If you wanted to put the 1 there, that's fine. So that would be the most technical way. but it's understood because of the ring. You have to start numbering the ring at the double bond. It's understood that it's at carbon number 1. And so furthermore, it would you typically wouldn't see cis and trans in the double bond, because if you had a double bond in a ring, so the hydrogens are here, right? So technically this is cis, because that's priority. If you split the double bond this way, it's 1 and 2, that's 1 and 2, so that is cis or Z. So in the ring alkene, you typically wouldn't see cis and trans illustrated or shown, because it's just understood what the double bond looks like. Because if the double bond was trans in a ring, it would have to look like that, and that is geometrically so unstable. It's geometrically impossible unless the cycle alkane has a lot of carbons in it. If it's a small ring, then there's no way that you can make those type of bonds with a trans double bond, so because it's just too unstable. So it's just understood what double bonds in rings look like. So sometimes cis and trans is not shown, but you might as well go ahead and show it just to be safe. Okay, so if we name these two, this ring, so it doesn't matter which carbon you pick. So if we pick that carbon though, then you have to number through the double bond. So you have to go 1, 2 that way. You can't say 1, 2 that way. You have to number through the double bond. So that would be 1, 2, 3, 4, 5, 6, 7, and 8. So this would be cyclooctane. And 4 double bonds, so it would be a tetraene. So we could say cyclo 1, 3, 5, 7 tetraene. Okay, so for this molecule, 1, 2, 3, 4, 5, 6, 7. So this is another diene, so it would be, and there is no cis and trans here, right? Because the 2 double bonds on one side, you don't have 2 different groups. So there's no cis and trans in this double bond. So we would have hepta, 2, 3 diene. And then on carbon number 4, you have an ethyl group. So 4 ethyl. Hepta 2, 3 diene would be the name of that molecule. Okay, so for this cycloalkene, so if we call that 1, 2, 3, 4, that would be one way to number it, or we could number it 1, 2, 3, 4, 5, 6. But that's not going to be correct, right? Because you want to keep the numbering scheme as low as possible. So the red is better than the blue, but what is also not correct is if we numbered this carbon 1, we can't go 1, 2, 3, because again, you have to number through the double bond. So if this 1 purple is number 1, then you have to number through the double bond, and that would match then the blue. So we can't number 1, we can't go 1, 2, 3 that way, because you have to go through the double bond. So the best numbering scheme is going to be what's in red. So this is going to be a 3 bromo. Oh, no. It's going to be what's in red. So it's going to be 4 bromo. Cyclohexene. Or if you wanted to put everything in, the Z, but again, since it's a ring, it's understood what that double bond looks like. But Z, 4 bromo, cyclohex 1-ene would be technically the way to name the molecule, but a lot of people would just name it like that because it's understood what that double bond looks like. Okay, a couple more examples. So if we throw in some stereochemistry, RNS, so that's a chiral carbon, so don't forget about your RNS. So that's carbon 1, 2, 3, so that carbon is R. And for your double bond, this is priority 1, that's 2, bromine is 1, carbon is 2, so that is a cis or Z double bond. So put your stereochemistry at the front. So where are we going to number this from? So let's decide left or right. So we want to keep the alkene as low as possible. So 1, 2, 3. If we number from the right, the alkene's at number 3. If we number from the left, it would be 1, 2, 3, 4. 1, 2, 3. It would be at 4. So we're going to number from the right to keep the alkene as low as possible. So this is carbon 4, 5, 6, and 7. Okay, so let's see. So we have a 6R, and carbon number 3 is a double bond, and that is Z. So that's the stereochemistry for the chiral center and the double bond. And then we have a 4-bromo, and then a 6-chloro, and a 2,2-dimethyl. And then 7 carbons would be hept. So hept and the carbon-carbon double, so heptane, but it's going to be a heptene because of the double bond, and the double bond starts at carbon number 3. Right, so the A would, for heptane, would change the E to be heptene and put the 3 right before the E to indicate that the double bond starts at carbon number 3. And that should be the name of the molecule. Okay, so if we name these two, let's see. So 1, 2, 3 would be R. 4 is on the solid wedge, so we have to reverse the arrows. So the stereochemistry here is S. And for the double bond, that's priority 1 and 2, and that's 1 and 2. So ones are opposite, so the double bond is E. Which side do we number from? So 1, 2, 3, 4. The double bond starts at 4 if you number from the left. 1, 2, 3, 4 starts at 4 from the right as well. So then we're going to go to substituents. So the first substituent would be at number 2 if we numbered from the right, whereas it would be at number 4 if we numbered from the left. So we're going to number from this side. That's 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So carbon number 2 was S, comma, carbon number 4 is where the double bond starts at, and that is E. So 2S4E is the stereochemistry. And then we have a tert-butyl, which is alphabetized based on B, and we have a difluoro, which is alphabetized based on F. So the tert-butyl is going to come first in the name, so 5-tert-butyl. And then 2,4-difluoro. And octane would become octene, so oct-4-ene would be the name of that molecule. Okay, this one, so we have 3 double bonds, so we need to take the stereochemistry for each one. So 1 and 2, and the hydrogen is down here, so 1 and 2. So this double bond is Z. 1 and 2, and the fluorine's 1, and that carbon is 2. So here that one is E, and this hydrogen is down there, so that's 1 and 2, and that is 1 for this carbon, for this alkene, and 2. So here the ones are opposite, so this is going to be another E. Okay, now which end to start numbering from? So 1, 2, so the double bond, first double bond's at 2, whether you start from the right or the left. And if we started from the right, then the first substituent would be at carbon 1, 2, 3, the 3-methyl. If we started from the left, the first substituent would be at 2, the 2-chloro. So we're going to start numbering from the left. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the stereochemistry. So carbon 2 is Z, carbon 4 is E, referring to that double bond, and carbon 6 is where the next double bond starts at, and that is E. So that will be the stereochemistries for the double bond. Okay, so then we have 4-bromo, 2-chloro, 6-methyl, and octa. So again, when we have more than one double bond, you typically keep the A to make it easier to say. So octa, and then double bonds start at 2, 4, and 6. Triene would be the name of that molecule. Don't think I made any mistakes. Okay, so lastly, what you could be asked to do is, for example, to draw E2 pentene. So if you wanted to do something like that, so you're given the name, draw the alkene. So 1, 2, 3, 4, 5. And double bond has to be at carbon number 2. So let's see, if we drew this, so if we put a hydrogen there and put a hydrogen there, then that would be trans, right? That would be E. Of course, if you did this and you're asked to draw cis 2-butane and you did that to begin with, you would know you need to just change 2 groups. So if we let's see. So if we were trying to draw cis 2-pentene instead, well, that's trans, so let's just change these 2 things. Now it's cis. Right, so that would be 1, 2, 3, 4, 5, cis 2-pentene. Okay, that's how you name alkenes, and that's how you do cis and trans.